All right, guys, this is our last video on organic chemistry. So we're going to talk about aromatics. All right, so let's just have a look at this. So the first question when you're talking about aromatics is probably, what do you mean aromatics, right? What is aromaticity? So quite simply put, all right, aromatic compounds have delocalized electrons around their pi orbitals, right? That's the simple definition there. And I really want the black pen. Okay, thank you. And I actually have a model of Buckminster fullerene. It's this great big carbon ball that I keep in my classroom. And Buckminster fullerene would be a very complicated example of an aromatic compound. But the simplest aromatic compound is just benzene, which you can actually see right there. There's a 6-carbon ring. 1, 2, 3, 4, 5, 6 goes right around through there. Okay, so that would be a benzene ring. Now, when we say the electrons are delocalized, what does that mean? Well, electrons move, electrons move. Yes, electrons do move. That's a great point, Coach Rednauser. Thank you. All right, let me rewind that thought. Electrons are involved in bonding. And single bonds, which we call sigma bonds, you can see them right here. They're the bonds we've talked about most this year. And in this diagram, they're red. And single bonds are not delocalized. They can't be. If they were delocalized, they would no longer be involved in bonding. But above these sigma bonds, the carbon atoms have pi orbitals. And remember, the orbitals that are, found for each atom are slightly different. But when we're talking about the carbon orbitals, these p orbitals are oriented in such a way that when you have carbon bonds in a relatively flat structure like benzene, these pi orbitals kind of stick up above the molecule, and these here in white stick down below the molecule. And the electrons that form the double bonds in benzene, right, we might draw them, say, here and there and there. Those electrons are bonding in the pi orbitals. Now the problem is we can either draw benzene like this with alternating double bonds, or we can draw it like that. And you can see here pretty easily that the double bonds have rotated, they've moved. And there's not really that one is right and the other is wrong. It's actually the fact they're both true. And they give us a hybridized benzene that we might draw with dotted lines, or sometimes we'll show it like that. All right. Either way, what we're trying to indicate here is that there's resonance that is occurring. Those electrons are moving around. And so you can kind of think about them like it describes the electrons over here. They're kind of smeared across these pi orbitals. And so all of this is now a bonding region. And that's what gives many of the all of the aromatics, many of their characteristics, their traits, their chemical properties, their physical properties. And one of those properties is the fact that they have a distinct smell. The smell may change, but it has a smell. You can smell them. And so that led to the name aromatics. Now, as far as naming them is not really any different than our regular cyclic aromatics that we talked about already. So things like 1-ethyl, 3-methyl benzene. We should be able to name that, right? We have benzene. That's right come back here. There we go. At position 1, we have an ethyl. At position 3, we have a methyl. So just like we have been naming, that doesn't change. We want the largest side group to have the biggest name. We want the alphabetically first side group to have the smallest number. Wow, stumbling all over myself here. Ethyl starts with E, methyl starts with M. So E comes first, so that's number 1. Position 2, position 3 is methyl. And so I have 1-ethyl, 3-methyl benzene. Now, here in the middle, I have 1,3,5 triethyl benzene because I have ethyls at all 3 points. And it doesn't matter if I label it that way or I label it that way, or I label it however, as long as one of these has a 1, right? Because it needs to have the smallest possible number. Over here on the right, we have one that's a little different. It's not really a functional group. It is a functional group. It's not a functional group made of other carbons. It's actually a halogen functional group, and so we just call it chlorobenzene. We could put an F there and call it fluorobenzene. We could put a Br there and call it bromobenzene. All of those would be fine. Now, there are some important aromatics. There's a chart of these in your book. Naphthalene is pretty important, this one right here in the middle. We use it in mothballs. We use anthracene in pigments. Indole is both important in the indigo industry, but also in creating cell molecules that signal, like the cell signaling molecules, that signal back and forth between cells. So when we try to create drugs from scratch, like medicinal drugs, a lot of times we might find an indole ring is necessary. Chimney soot has this benzopyrene in it, which was actually the first carcinogen ever discovered. And then toluene is also a really important solvent. Xylene's also used in polyester. I mean, y'all can read, right? I'm just reading these off here. These are all important aromatics. So they're, very common chemical compounds that we see in our day-to-day. Now, that's going to pretty much wrap up our description of organic. Organic can get very complicated. I mean, you can go on and have a career in organic chemistry. These are some things you might see. So this is called the Corey-Fuchs reaction. It's something that I learned about in college, right? It's just an organic reaction, right? It involves a halide, which is a special kind of molecule, and you form a dibromoalkene with the Wittig reaction. Loads of fun, right? You track the electrons moving. You can kind of predict where things are going to go. It involves a lot of an understanding of, aromaticity, the movement of electrons, electrophiles and nucleophiles, like are electrons going to attack a certain region, why or why not? Very interesting stuff. But if you want to learn more about organic, go take organic chemistry, all right? If you have any questions for me, shoot me an email. I'll be glad to give you guys a hand. But other than that, that's going to wrap up our discussion of organics. So a nice little short video to end the week.